These are the three types of nuclear decay. This is it, to my knowledge. Alpha decay is the emission of an alpha particle. We also look at alpha particles as being helium nuclei, just the nucleus part. Beta decay is also looked at as being an electron, and gamma decay is just a photon. Alpha decay loses 2 neutrons, loses 2 protons. That one's really straightforward, Himparus. This one's really quite straightforward. They just leave the nucleus. The 2 protons and 2 neutrons that were there just go for a drive. That's normal. The weird one, the really weird one, is beta decay. Because in beta decay, a neutron spontaneously turns into a proton, and when it does, an electron just pops into existence and goes for a ride. This isn't an existing electron that leaves. That would just make it an ion. This is a brand new electron that did not exist before, springs into universal existence, and just shoots off into space. Which is weird. That should make you uncomfortable. Neutron becomes proton, electron springs into existence and goes for a drive. Lucas handles first and then Himparus. Yeah, there's more in the box. Himparus. Yep, that is the question that nobody asked me yesterday. It just does. So a neutron is, so where we don't get into things, I'll briefly talk about these things now. Neutrons and protons are not the smallest bits. You can get smaller bits. You can get things called quarks. And neutrons are made up of neutrons and protons are made up of 2 kinds of quarks. And just so I don't screw this up, because it's been a long time, I will look this up. Just so I don't mess this up for you. Quarks in neutrons and protons. So, a proton contains 2 up quarks and a down quark, and a neutron is 1 up and 2 down. Himparus. So a proton is 2 ups and a down. So we're really clear. I'll draw this up for you. Proton, neutron. A proton is made up of 2 up quarks and a down quark. A neutron is made up of 2 downs and 1 up. So they're exactly opposite. 2 ups, 1 down, 2 downs, 1 up. This is your proton, this is your neutron. Different question. Unrelated. We'll get to that. So in order for a proton to become a neutron, really all that has to happen is one of these quarks needs to flip. If one of those quarks flips and becomes a down quark, all of a sudden this proton is no longer a proton, it's a neutron. Yes, that is the correct sentiment. She sits there and I don't like this. You shouldn't. This should make you feel wildly uncomfortable.
So what kind of energy does that have to write?
It's a great electron. In order for that flip to occur, an electron needs to spring into. So you want to know what an electron is? Here's an electron. Yeah, this is what we did yesterday. Okay, so Himparus, here's another step for you. So these quarks, like a proton is partially charged, the quarks are charged too. So the quark has, every up quark has a plus 2/3 charge. I don't know why, that's just the way it is. So up is plus 2/3, and down is negative 1/3. What do you get when you add 2/3, 2/3, and take away 1/3? You get 1. So that is why the proton has a charge of 1. If you look over here, what's with the neutrons? Well, the neutron, this is going to be plus 2/3, that's going to be minus 1/3, that's going to be minus 1/3. What happens when you add 2/3? You get 0. That's why a neutron has no charge. Because the quarks here cancel each other out. Here, they add to 1. That's why protons are charged, except not. So when you, and then what the heck's going on with an electron? Well, let's look at the electrons. What is an electron? So an electron in Paris is, I just want to make sure that I was right on this, an electron is an elementary particle. So like a proton and neutron are not elementary particles, they're made up of quarks. An electron, being an elementary particle, is not made up of anything else. An electron just is an electron, charge -1. Where does what?
Where does it get like this negative, not negative?
The negative chargedness of it all just is. That is just a property of, it doesn't come from anywhere, it comes from being an electron. How does an electron form during beta decay? Okay, so in Paris, you asked this question here too. This is going to bother you in Paris. There is no good reason. It just does. We just know that it does. Something needs to leave, carrying away the energy that was released in the swap, and that thing that takes away the energy is an electron. The other part to this is there's actually two kinds, which we're not going to get into. There's actually two kinds of beta decay. There's beta plus decay and beta minus decay. We looked at beta minus decay. In beta minus, you get an electron. You also get another particle that I didn't tell you about, but you get an electron. And in beta plus decay, you get a positron, which is the opposite of an electron. But again, we were not going to go into this. Yes? A positron is like an electron. It's a fundamental particle. It's the opposite of electron. It's another elementary particle, yes. Yes. And the other particles that I didn't tell you about that beta decay produces, in beta plus you get what's called an antineutrino. Sorry, beta minus you get an antineutrino. And in beta plus you also get a neutrino. But we don't talk about the neutrino portion of it in Science 10. Things get weird. We keep it simple. As simple as we can while still being truthful to it all. Where did that picture go? No, come back. Okay. Okay, so let's go over the homework. This is what it looked like yesterday. That chart up top here was the first piece to this. Lamise and are we almost done with our makeup? That'd be great, thank you. Alpha, beta, gamma decay, there it is. In alpha decay, Malik, number it. You were away yesterday, you should be paying attention to this. Alpha decay, you lose 2 neutrons, lose 2 protons. Beta decay, you lose a neutron, gain a proton, and you also lose an electron. And then gamma decay, you lose nothing. It's just energy. Well, you don't lose any particles. It's just energy that goes for a ride. So this is what the bottom of that sheet should have looked like. Alpha, beta, alpha, gamma, gamma, beta are questions 1 through 6. And then 7 through 13 are down there. It asked 7 to 10 asks you to write the alpha decay equations. 11 and 13 I don't know where 12 went. 11 and 13 asked you for the beta decay equations. Comments, questions, concerns on that page? Going once, twice, thrice. So yes.
You explain like how to get the first one and beta. I put CF.
Okay. So where I would say, so the next page I think has got similar kind of questions. So what I did, maybe I made a mistake. At 256, so I wrote down the decay particle first. So He, or you can write it as alpha. I did 1 as 1 and 1, or 2 as 1 and 2 of the other, just to show you they're equivalent. So the helium's 256 minus 4 is 252. 103 minus 2 is 101. And then I would have gone over here. Maybe I made a mistake. And I would have found 101. 101 is MD. So CF would have been 98. So you took off, oh, so what you're, no, I don't even know what you did. You would have taken off 5 to get down to 98. But good question, Liam. So no other questions on this front page? Going once, twice, thrice, so. Okay, cool. Here are numbers 1 through 12. Take a look. Comments, questions, concerns. Compare what you got with what I got, Luca and Dennis. Put your phones away. Okay, no questions. Okay, here's the bottom ones. 13, 14, and 15. If there are no questions, it means either you guys are all amazing or that you didn't do your homework. So, yes, Malik. Number 7, yes. Okay. Memphis, Imparis, Malik's got a question. Number 7, Malik. Yes, go. Okay. So, just like when we were balancing equations, we have the same number of stuff on the left as we do on the right. So we had 216 mass and 84 protons on the left-hand side. We still need those total numbers on the right-hand side. So if a beta particle has 0 mass, then the 216 has to stay the same, because something plus 0 is going to be 216. For this number down here, the 85, 84 is what we started with, and -1 left. So what plus -1 is going to give you 84? That's the 85. 85 plus -1 is where the 84 is going to come from. So then you have 216 and 85, and then once you figured out that this is 85, that's when you go and you flip to the periodic table and say, okay, cool. What the heck is 85? 85 is astatine. So then AT is the symbol that goes next to it. Start with the decay particle. Figure out the mass and protons that have to be present, and then go for the symbol. Okay. Questions, comments, concerns about anything further? Once, twice, thrice, sold. Okay, cool. Then I'd like you to flip ahead to this. Nuclear energy. Let us talk. So this whole unit's been about energy. Nuclear decay doesn't really sound like it's going to be a conversation about energy, but it is. Let's talk about why. So, recall, high energy isotopes will release extra energy through alpha, beta, or gamma decay. If you are able to destabilize an atom, either by adding mass as a neutron, or by adding energy, if you're able to destabilize it, you're going to get a situation where decay is going to occur. That makes these particles radioactive. That's the connection here with radioactivity. Particles or radiation may be released during this process, and we can transform this energy, the particle or radiation, we can transform that into different forms of energy. In this lesson, we're going to examine how we can take nuclear energy and transform it into energy that we can use. There are two nuclear reactions we're going to look at. The first one is nuclear fission. This one was the first one that we, as a human race, discovered. In nuclear fission, a heavier nucleus, a bigger nucleus, in this case, uranium-235 is the big nucleus that we're going to start with. We have discovered that this nucleus can split into smaller, lighter nuclei with a release of energy. And you might say to yourself, huh? So here's what happens. It's a slightly different kind of decay. So uranium-235 is inherently unstable. It's not like really unstable, but it's unstable enough that it's going to be radioactive, and it's going to be radioactive for a really long time. Uranium takes a long time to go through its decay process on its own naturally. I showed you the decay chain for nuclear, or for the nuclear decay for uranium. That's what's on the board over there. On its own, that's what uranium will do. Uranium becomes thorium, thorium becomes something else, all the way down until all the uranium is gone and you're left with a hunk of lead. But because uranium is inherently unstable on its own, you can kick it, and not literally kick it, but you can slam it with something else. In this case, a bonus neutron, and you can start it, because it's unstable on its own, you can push it over the edge and really make it go a different pathway. Yeah, take your gum out, do what you got to do. Share with the table, I suppose, get it done. Okay, and so uranium isn't going to do its normal decay chain. It's like if you have a friend who you know is a little bit on edge emotionally. If you've got a slightly, kind of an emotional friend, they're going to deal with their emotions their own way. They might be outbursts. You might see them. It's like when Mr. Keeley. Mr. Keeley and I are buddies, and I don't know if you've ever noticed, but sometimes Mr. Keeley will walk in here and say, Mr. Dweedoff, what kind of pepper day is it? And that's our code. So we both like the restaurant Earl's, and there's a dish that you can get at Earl's called Hunan Kung Pao chicken. Well, Hunan Kung Pao, and you can put different proteins in it. I always get it with the chicken. When you order this at Earl's, they will ask you, how many peppers do you want? And that is their way of asking, how spicy do you want this thing? You can put as many peppers in as you want. I like 3 peppers. 3 peppers to me is a good amount of heat, and I can still enjoy the dish. So Mr. Keeley will walk in and be like, hey, so if I seem a little on edge, he'll ask, how many peppers is it? That's a way of asking, Dweedoff, how spicy are you feeling today? How ticked are you? And Keeley and I will ask this question to each other. And on our own, like normally, level. We're pretty level. But there are things that can happen that can, if I have a rough morning with the kiddos, I might show up to school already a little bit on edge. And if nothing else happens, I will deal with my on edge, and it will just kind of go, it'll decay on its own. But if I walk in having already had a rough morning with Jack and Natasha at home, and I roll in here and something sets me off on the way, it's like getting this bonus neutron where I would just decay my emotions naturally. Something else showed up, and now my emotions are going to decay, but they're going to decay a very different way, perhaps a slightly more explosive way than they would have decayed on their own. So that's what's happening here. With nuclear fission, if you are able to kick a block of uranium-235 with a bonus neutron, what's going to happen is that uranium, the atom is going to split. It splits into krypton and barium. The whole nucleus just kind of goes rip, and 2 different nuclei shoot off into the world, krypton and barium, or barium rather. And if you look at the mass here, you get 36 and 56. 36 plus 56 is 92. So the protons add up, but the mass, 92 and 141, is you're short. 92 plus 141, this mass here and this mass here is 233, but you had this bonus one here, so we need 236 mass here, and you only have 233 mass here total. So something else has to go, and that something else is 3 bonus neutrons. So 1 neutron went in, 3 bonus neutrons are coming out. And so the really interesting thing here is when you have a hunk of uranium, it's not just one atom. This represents 1 atom of uranium. When you have a hunk of uranium, you got a bunch of these U-235s. U-235, U-235, U-235. There's a whole chunk of them all over the place. U-235 surrounding the other nuclei you have here. And so what's going to happen is all you need to do is you need to send in 1 neutron. And then when that one neutron hits the uranium, 3 more neutrons are going to form. One of these is going to hit that guy. One of them is going to hit that guy. One of them is going to hit that guy. And each one of these is going to launch 3 more. One of these might hit this guy. He's going to launch 3 more. One of these is going to hit that guy. He's going to launch 3 more. One of these might hit that guy. He's going to launch 3 more. And so all of a sudden you get this chain reaction of nuclear decay, and this happens very, very quickly. And in addition to these neutrons, there is a massive release in energy. Do what you got to do. If this happens uncontrolled, what do you get? This is the first nuclear bomb. Yes. If this is uncontrolled, all energy releases at once. And when you have all the energy releasing at once, that is by definition a bomb. Yes, Simparis.
So like by control, like do you like reduce the amount of like atoms of uranium, or like
No, you don't reduce the atoms of uranium.
or do you just make it go one at a time?
You make them go one at a time somehow. So you don't have to we do, because you don't. Both. The short answer is both. We use a smaller amount of uranium, and the real problem here with the uncontrolled nature of it is all these bonus neutrons. If you can figure out a way to contain these bonus neutrons, then the reaction doesn't go uncontrolled. If you only let 1 out, then that guy's going to hit that guy. And if you can control these 2, then that guy's going to hit that guy, and then that guy's going to hit that guy. If you can regulate how many neutrons are released, now all of a sudden you can take this uncontrolled explosion and you can focus it and you can say, 1 at a time, you can go, and then you can go, and then you can go, and then you can go. And now all of a sudden this fuel, instead of getting blasted in one large explosion, can last 25, 30 years. Yes? So, let us flip the page. What is the solution? That is the question. So this is a diagram of the chain reaction I just described. A nuclear fission reaction releases free neutrons. These free neutrons can collide with other nuclei and continue to split them, resulting in a chain reaction. This is a uranium. This is what I drew before. So uranium-235, the chain reaction is going to look like this. A single uranium-235 is going to get hit by a neutron. Barium, krypton, and 3 neutrons are going to result. This is what we had on the previous page. Some of these neutrons are going to hit other things. And then the free neutrons might not, uranium doesn't have to split into baryon and krypton. As long as the mass and protons are conserved, it can turn into other things. Like rubidium, and cesium. So then you get another bunch of neutrons being released, or maybe it splits into xenon and strontium. And you get more bonus neutrons released. All of these things, these bonus bits that are getting released here, all of them themselves are also radioactive. These things, the things I just circled, if you're familiar at all with the development of nuclear weapons and nuclear science in the 40s, 50s, and 60s, 1940s, 1950s, 1960s, and video games, if you're familiar with video games, one of the terms you might be familiar with is the term fallout. That term fallout refers to all of these things, the barium, the krypton, the rubidium, the cesium, the xenon, and the strontium, that are all in themselves radioactive, that these bits now all get spread. In this explosion, all of these bits get spread out into the atmosphere, and the atmosphere wind carries these things to other places. And you get radioactive fallout in places that the bomb itself didn't actually touch. So that word fallout in the video game title refers to this. Nuclear debris getting spread all over. So the really scary part here is all of this extra energy. This is what gives you the devastation that comes with a nuclear blast, not the particles themselves. All of the extra energy that results when these atoms split is what is the terrifying part of the nuclear detonation. For nuclear fission of U-235, a chain reaction results in many nuclei fission or many splitting of uranium. This dramatically increases the amount of energy transformed. And it gets transformed. The interesting thing is where is it coming from? There is energy that holds these particles together. And by breaking the particles, that energy needs to go somewhere. And so it just goes out into the world and levels whole cities. Additionally, this whole process gives off alpha or beta particles and gamma rays. So there are places. So gamma rays, I told you guys yesterday that gamma rays are just high energy light. Soham, stop talking, please. Just high energy light. Light makes shadows when you block it, right? Like here's you can see the shadow of my hand on the paper underneath, even though my hand's not touching the paper. There are places in Japan, because Japan has the unique distinction of being the only country on the planet where nuclear weapons were used in war against people. There are places that you can go to in Japan where you can see the shadow on the wall of the person where they were standing when the nuclear blast went off, and their shadow remains on the building forever. Because they blocked the wall from receiving all the gamma radiation that the rest of the wall around them, around their shape, received, and their body took all that gamma radiation and got vaporized. They just went from there to dust as a result of the nuclear blast. There are places that the two cities are Hiroshima and Nagasaki. Those are the two cities that were bombed by the Americans in World War II. And there are places you can, to this day, and they are kept as a remembrance of, this is why we don't want to do this. The devastation that is results. The shadows still exist, because this is just high energy light. Karndeep, yes, you may. There was actually not really a fun story. There was a story. There's one person that we know of that was actually at both sites. He was in Hiroshima the day that Hiroshima was bombed. He survived, and he's like, I have to get home. He wasn't from Hiroshima. He was from Nagasaki. And so he recovered, got on a train, went home, and 2 days later was in Nagasaki when that bomb went off. So he's the only person that we know of that actually survived multiple atomic blasts, and he died at like 70 or 80 years old. Like he lived the rest of his life to old age, surviving both atomic blasts. I don't know what that does to a person's psyche, but that is something. Okay, so Himparis, I'm going to answer your how do we control this question later. Here we go. Nuclear fusion is the other one. Believe it or not, nuclear fusion is worse. So, it's actually more interesting though too. Nuclear fission is the splitting of something heavy. Nuclear fusion is in nuclear fusion, two very small nuclei fuse together to form a slightly bigger nucleus. So it's the other way. Fission, takes something big, splits it. Fusion takes something small, slams them together. And the ironic part is, when you take the smaller things and force them together, you actually get more energy released than when you took the big thing and split it. They both release energy, but you get more energy when you force the little things to come together. The bonus part of the forcing little things to come together is you get way less bonus radiation. All that extra fallout that we got from fission, you don't get with fusion, which is why we're trying to attain fusion. This is something that we as humanity want to do, because we recognize that if we are able to control fusion the way we can control fission, then we will get a much safer form of nuclear energy, where the products aren't radioactive. They're just slightly heavier nuclei. So let me show you how this happens. For nuclei to fuse, they need to collide with a lot of force. They need to move very, very fast. This also needs to occur at extremely high temperatures. When the nuclei fuse, they produce energy that can continue the fusion reaction. But this is difficult to control, and we have currently not been able to successfully do this. When we say not been successful, we can control it. We know how to control a fusion reaction. What we have not been successful in doing is controlling the nuclear fusion reaction with less energy than fusion produces. Right now, for example, if a fusion reaction creates 100 energy, we need to put in 200 energy to stop it from going crazy. And so as long as we're taking more energy to control the reaction than we get out of the reaction, it's not going to be a viable energy source. That makes sense, right? Okay, we're spending more energy to stop it from ripping our planet apart than we can get out of the reaction. Nuclear fusion right now, in its only controlled, or in its only naturally controlled state, happens in the sun and other stars. Nuclear fusion is the fuel that stars use to be. The reason that they're bright, the reason that we can see them, the color that they are, is due to this process. And they change color depending on what they're fusing. So as the fusion reaction happens, so here's what you start with. Fusion starts with hydrogen, hydrogen 2 and hydrogen 3. These two things fuse together, and they create helium. Helium with a mass of 5, not 4. And so then what happens is that as these guys are hanging out here, fusing, helium shows up, and then helium, unstable, undergoes decay and boots out that extra neutron and becomes helium-4, which is stable. This is stable. This is a free neutron again. And free neutrons are the problem. So what stars will do is stars will undergo hydrogen fusion until all of the hydrogen has been used up. And then what's left over after all the hydrogen has been used up? Well, it's a bunch of helium. So then stars will then start to take the helium. And the helium, being a heavier element than hydrogen, will sink to the center of the star because of gravity. And then when it gets to the center of the sun, all that helium starts to stack up and then it starts to fuse at a higher energy. So now you're getting more energy released because helium is fusing. And then once the helium is done fusing, if you look at the thing, helium is 2, so 2 plus 2 makes 4. If you take, what is the atomic, or what is the element that has an atomic number of 4? Luca and Dennis, please stop. Luca, maybe you can answer the question. What's the atomic nucleus that has 4 protons in it? It would help if you flip to a periodic table. Dennis, you could help him out. 4 protons means the atomic number is 4. What element has atomic number 4? Sorry, beryllium. Yes. So hydrogen starts fusing, then the helium fuses. When all the helium's done, then beryllium. And these things get bigger and bigger and bigger and bigger, all the way down into the metal section, where you start to fuse gold. So there's tons of gold that is actually produced in nuclear fusion in stars. And when those stars then explode, Himparis, stop talking to Vikram. When those stars explode, that's when gold and other heavy elements scatter throughout the universe. So the amount of energy released in a fusion reaction is about 10 times less than the amount transformed by fission. But because hydrogen and helium are much smaller in size, the energy released per unit is larger than fusion. Is larger in fusion, rather. Because it's easier to get so much more hydrogen packed into the space that the same amount of uranium would take out, you actually get more energy from the equivalent mass in fusion. Also, the products of nuclear fusion are not radioactive. Radioactive isotopes. They're just helium and a neutron. So there is no radioactive. Oh, the pen is bad. Radioactive nuclear waste in fusion reactions. This is what we'd like to try and avoid, is the nuclear fusion. Okay. Give me 1 sec. Okay, so when you're ready, flip the page. This page here, I would like to get to the answer to Himparis' question. So this page right here, we're not going to talk about today. This is going to be a homework page. I'd like you to flip one more time, and I'd like to do this page here today. So how do we use nuclear energy? Okay, so Himparis, here it is. Nuclear reactors transform. Here's how we use this. Because in fission, there's a ton of thermal energy created in a nuclear fission reaction into electrical energy. What we do is, take a look at what's going on here. We have these fuel bundles in this picture down here. And these fuel bundles are the uranium. There is, Malik and Soham, stop talking, please. You'll see here at Himparis, it's labeled, there's a thing labeled control rods. These control rods are the key. So these control rods, I want to make a line over here. Those control rods are made up of things like silver, cadmium, and a thing called boron carbide, And these things, these control rods, these particular elements, okay, there's way too much talking going on underneath what I'm trying to say. Silver, cadmium, and boron carbide, these guys are really good at absorbing neutrons. And so when you place them in and amongst the fuel, you absorb the neutrons that would have otherwise gone and hit another uranium. So you throw a control rod throughout the fuel. You mix it throughout. And all of a sudden now, this neutron doesn't hit another uranium. This neutron doesn't hit another uranium. It gets absorbed by these control rods. And the only neutron that's allowed to go through is that guy there. He's going to hit one of these guys. And again, you're going to have control rods spread all throughout your fuel, absorbing bonus neutrons that come close. They're attracted to these control rods. And so as a result, you get the slow nuclear decay that releases a usable, manageable amount of thermal energy. Generally, so I'll fill in this blank up here. Generally, reactors use uranium-235. If there's enough uranium-235 present, then the neutrons emitted in fission will start the chain reaction, and the control rods will slow down that chain reaction. Just to give you perspective on this guy down here, one singular pellet is the size of a thumb, like your average adult thumb. So there's my thumb. One of these uranium pellets is about that big and is worth, it has the same amount of energy contained in it in about 844 liters of gasoline. So my fuel tank on my Corolla is a 45-liter tank. It means I would have to fill up my car 19 times. So I fill up my car every 2 weeks because I don't drive it a lot. So 2 weeks times 19 times, that's 38 weeks. 38 divided by 4, that's 9.5 months. A single one of these pellets would theoretically fuel my car for 9.5 months. And there's tons of these little pellets in one of these reactors. So these reactors, anything that's powered by these nuclear reactors, theoretically has fuel for decades. It's like an American nuclear aircraft carrier is fueled by 2 or 3 of these nuclear reactors. They can stay on the ocean for 25 years. Okay, that's it for me today. I'm done. This page is your homework. We'll finish this up tomorrow. Imparis, yes, what was that question, sir? Heavy water. Great question. Heavy water is something called deuterium. It's not H2O. It's, oh, hold on here. Okay, so heavy water is, okay. Okay, so, Imparis, let's come over here so I'm not yelling over everybody. So regular water, you have H2O, and each of these hydrogens is hydrogen 1. Standard hydrogen. In heavy water is called deuterium. And deuterium is still H2O, but it's not hydrogen. It's hydrogen 2. So deuterium is hydrogen with a bonus neutron. So instead of having, really, what hydrogen 1 is, hydrogen 1 is just a proton. So this is an oxygen bonded to 2 extra protons. This is oxygen bonded to 2 proton-neutron pairs. temp water. And it is cooling regulated temperature.
So like the mass is
Sorry?
so the mass is increased by
Yes. With a bonus neutron. And you can actually swim in it. It's safe to swim in. Today's Tuesday. Oh, it'll be Monday. Okay. Over right behind you. If you wouldn't actually mind sliding that back, that where it goes, that would be lovely.
This one?